Good morning, good afternoon, good evening. Welcome to TESI, my YouTube channel for theoretical and experimental scientific investigation. Today, I will guide you through the identification of the electromagnetic wave produced by a Stator field. Before to start this conversation, I would like to thank Lab Center for providing a free license software for Proteus, a powerful PCB software design that allows also to perform simulations for experimental validation. The agenda of today is characterized by the introduction of one motor R's, the equations that we're going to use to identify the electromagnetic wave, the tools in order to capture the voltage signal, and the experimental results that allows us to give the full parameterized equation of the electromagnetic wave. Now, motors are electromechanical converter. We inject current in the coil, and through a particular mechanical design of the entire system, so the current interacts with the magnetic field to generate torque and or force. All right, so the motors can be used by a DC current and AC current. In the DC, we have a constant signal affected by ripples. Usually, they are like a noise and disturbances. Or we can use the alternating current. Those are characterized by a voltage signal typically in a sinusoidal fashion. So as all the sinusoid, we have frequency and amplitude in order to characterize the signal. The equations that we are looking at right now are called Maxwell equations. These equations are characterized by mutual interaction by time and space. In particular, in the first, we can say that any spatial variation of the electrical field is associated a time variation of the magnetic field. The second says that a spatial variation of the magnetic field is related to a time variation of the electrical field plus a distribution of current. The third equation says that the flow of the electrical field is characterized by the ratio between the free charge space over the dielectric constant that changes according to the mean where the electrical field is traveling to it. The fourth equation says that the flow of the magnetic field through a closed surface is always zero. Have you ever imagined, for example, when you get the magnet and you break it to pieces, you're not going to create just the north or the south. You're going to create both. So that means that you cannot have a single magnetic pole. Okay, now starting from this, we're going to proceed to the next slides. So by pre-multiplying the first one, all right, which we are going to represent here, okay, for the curl of that, we're going to pre-multiply both members for the rotors of the nabla. Nabla vector is something that if you don't know it, better off you refresh in one physics books. This is not the right place to do that. Moreover, we have to remember the fact that the rotor of B that we have seen is the equation number 2, which appears also in the equation number 1 transformer for the car. So at that point, we have basically the transformation of the first equations like in a differential form in the space domain. The nabla power 2 is called Laplacian. The divergence of E has to be discussed with equation number 3. Now, we don't have any spatial charge distributed in a volume. So, by not having this one, the divergence of E is 0. So, sorry, the equation, the Laplacian equation, becomes like dependent on the current density and the electrical field. And that since there is the J omega in the front, okay, which is equal to the derivative in time, we have the Laplacian E is equal to mu the in the Tj plus mu epsilon the square in the T square E. This is a not homogeneous differential equation in two variables, space because of the Laplacian and time because of the time derivative. Now, we have to say something about the current density. The current density here, there are two kinds of current density. That one running through the wire, and that one basically distributing in the space. We don't have any charge traveling into the space at a certain speed by which we can have any current density traveling around. So it's unlikely that will not be used. The J source instead is the current running through the wire, where the current running through the wire is characterized by a certain number of electrons multiplied by the charge of the electrons and the speed. Now, since then we want to study the homogeneous solution of the equation because that represents the natural mode of the way the electromagnetic wave propagates into the space, we are posing everything j is equal to 0, where the Laplacian minus mu epsilon that square and that is square e is equal to 0. The equation 5, obviously, we have Laplacian. The Laplacian is a d square over dx square plus d square over the y square plus d square over the z square. And if we had to expand this equation in this form, we have basically three differential equations, homogeneous, sorry, because we have put 0 here. Now we have to make some simplification about that. All right, the simplification that we have to make can be possible only by performing some magnetohydrodynamic simulations. In particular, we have performed the magnetohydrodynamic simulations, in particular magnetohydrostatics, because we are basically doing a simulation where we fix the current value inside the coil in order to fix that in that moment, in that particular situation, what's the value of the magnetic field. It is possible to see that it is nothing that can be considered almost constant in these particular configurations, because we have a magnetic flow line all over whatever is the plane that we are looking into it. But by doing some simplification and simulation, we carried out some pattern that allows us to make some simplification in the rotor of B. We can see that the pattern, right, at first is characterized by an increasing, keep almost constant the value, and then going down. So, for what concerns, for example, the variation of the y component along the along the x direction, we are implementing, we are simplifying the discussion by saying that this is at 0. For what concerns instead the variation of the y component along the z direction, this cannot be 0 because e increase and then decreases. So the variation is stronger than the previous case. The same thing for what concerns the y component along the y direction, but this is not included in the curl of B. Now, for what concerns instead the z component along the y direction, this is completely 0, and moreover the order of magnitude is twice smaller. The same thing for what concerns the z component along the x direction, and then the x component along the y direction. Now, what happened? We have the last one, the x direction component along the z direction variation. So as you can see, the rotor B can be simplified furtherly. So we can say that the magnetic field law can be represented by the equation of B is equal to By as a function of the z and time, from where the cancellation. So we have B as a function of y, and implies what? E is equal to E of x, or rather a variation, a magnetic field which varies along the y direction in this way, generate an electrical field that has a sinusoid along the x direction. Okay, so by having said that, the number of differential equations that we have seen before reduced to only one. And moreover, since there are no variations on x and y, we have substantially the electromagnetic way to identify in terms of parameters like alpha and beta. After this general expression of the electromagnetic wave, there is also something that has to be introduced. The electrical and the voltage, the electrical field and the voltage produced by capacitor plates. This is something that you can find in every book, university book, or even high school book. All right, the benchmark setup is characterized by oscilloscope, capacitor plates developed by 3D printing and overlapping a copper film tape of a specific thickness, linked to a stator field, which appears here, and a transformer which is supplying energy to the entire stator field. Now, the 3D printed part are characterized by two plates where each plate is designed in order to have a gap between one little plate and the successive one. So when we put the copper tape on the top of it and we separate each plate, we generate the capacitor one to another from one plate to another. All right, so here has a specific design. We design the part, but remember, when you design the part in 3D print and something comes off, something is being deformed, so the measurements are taken like by accepting some imperfections. Even if you have here that datum structure where you design the component, pay attention to, because that things can vary. Remember, the electron is very small, and even if you change the position, the mutual position of these two plates, the voltage change. So we are accepting this one, this variation, just not to stop the analysis. Moreover, the benchmark setup for the component are stator field, which has coil electrical resistance of the coil and inductance. We have oscilloscope with a certain parameters, the capacitor plate that are characterized by the geometry, and a transformer loader with its input and output characteristics. We have performed some simulation by using the Proteus, where we have represented two possible connections, one in parallel and one in series, and we have depicted the frequency response of the two components. We extracted the points and we imported in a numerical software in order to understand what's the gain difference between the two kind of connection where the frequency is at 60 Hz, and we have discovered that basically we have a double of the current in a parallel configuration, something that we had to consider when we let the coil working on to prevent that they warm up excessively. Now it's time of test. We're gonna see what happened in the real life.
Alright, so what we have here basically are a set of instruments and the benchmark test characterized by the instruments like a multimeter that has to capture the voltage at the input of the transformer and at the output of the transformer, feeding the coils of the stator field. The stator field is characterized by two capacitor plates generated by 3D printing, where each station has its own screws where I can create conduction to measure the voltage directly injected in the oscilloscope. Now, here, this multimeter instead has to calculate the current running into this wiring system that, as you can see, is in its series configuration, because this is the series connectors and this is the parallel. We're gonna perform the experiments at first with the series and then parallel to see the main difference in terms of voltage and current supplied to the system. So, let's start with the series configuration and let's push the button. Alright, so we have 123.2 volt injected in the transformer, 4.8 volts coming out from the transformer, and with a current running in a series circuit equal to 5.54 amps. You have to notice that this is the target of the transformer. We have basically an 123 injected in a transformer that has the possibility to have 0 to 3400 volts. In the output, we have 12, 0 and 12. Now, it should be like 6 volts in the output, but unfortunately, and obviously, when you put an electrical load at the output of the transformer, the voltage goes down, and hence this is the value, the 4.8 volts, at that value of the current. Now, we have to do right now the difference in terms of the voltage carried out at two poles at the station, here on the right and on the left. As you can see, the voltage is the same, right? Now, I'm expecting that by increasing the distance of this probe right here towards along this line, the voltage injected is going to be different, and it will be lower by the time you increase the distance from the magnetic field source. Alright, so I'm gonna put this directly here in order for you to capture the difference in terms of voltage by increasing the distance. Sorry for this one. Alright, so I can put this one here, and okay, probably is better to give this one like here, like this. Alright, so you can see also myself that I am reducing the voltage by increasing the distance. So apply this one, and the voltage decrease. See that? Then I'm going to remove here again. Here I'm going to set up another distance. Take as a reference the division of the oscilloscope by the time that I'm moving, alright? It's gonna be different. So let me remove again this one. I'm gonna like this, and then I go forward. See, I'm gonna do like this, even farther. This is the voltage again. Okay, I'm not gonna move every time again, but let me move again, and again, and again, and again. As you can see, the amplitude is decreasing by increasing the distance from the magnetic field source. You see that? And again. So now I'm gonna get closer. Increase the intensity by decreasing the distance from the magnetic field source. Just give a look at the division. The divisions are those little square made by dots. See that? And now same distance. The same. See that? So the division are these things, are these dots. Vertical and horizontal. So vertical division and horizontal division. Alright? There you go. So the frequency, let's see if we can measure the frequency. Measure. We can do frequency right here. We have roughly 60 Hz, but let me tell you something, it's very difficult to capture the frequency with this kind of pattern, because we need to export this data in a numerical software and perform a polyfit that allows you to carry it out a more smooth sinusoid. As a matter of fact, it's so rough, the pattern, that even the amplitude has a certain difficulty to be calculated in these configurations. Alright? Now, next video will be made with the parallel configuration. So, now we have the parallel configuration. So, we have the same two measurement tools, the same components, but different connection. This time I'm using the parallel connectors right here, okay? And we are taking the measurements by using the oscilloscope and the multimeter for what concerns the input at the transformer and the output. Moreover, we have to pay attention when we create the connections, because we have to do the magnetic field in such a way that both coils generate the same magnetic field in terms of sense, right? It has to be the same sense, or both has to create a magnetic field that goes down or up. Otherwise, the magnetic field will be cancelled in the middle of the chamber. So, we are ready to fire up. I'm expecting double current, like before, like showing in the PowerPoint presentation. So let's fire up. So what we can see here, always the 120 to 121.8 volt at the input. This time the voltage in the output is even lower, and that happens because the current has been doubled in a parallel configuration. So if we take the measurements with the oscilloscope in the same fashion we have done before, all right? Let me set up this one a little bit properly so you can see the decreasing of the voltage. Okay, so same game of before. We're going to increase the distance of the analysis of the voltage. Okay, go forward, decreasing, again, 6, 7, 9, 10. There you go. It's going down. And by decreasing the distance from the magnetic field source, we have the increasing of voltage. Just watch the division again, and then this one, then this one, and then this one. Oops, it snaps. There you go. See that? Same voltage. I increase the distance. It's very small. I get the same distance of the channel 1, and I have the same voltage. So it's time to take this value, export this value in an Excel file sheet, and then try to build a polyfit that allows you to carry out exactly what's going on in terms of voltage, amplitude, frequency, and phase. I'll catch you later in the PowerPoint presentation.
All right, now that we have extracted the voltage signal from the oscilloscope, we can see a comparison between the original signal and that one obtained by creating a smooth representation. In the smooth representation, we are able to capture the frequency and the amplitude at a different station, or rather at a different distance from the magnetic field source. For example, Z 145 millimeter is the distance between the last station from the source. Each signal have been implemented in an FFT analysis in order to understand what's happening with the signal in terms of frequency contents here along the frequency span and the amplitude. As you can see, there is a decay of the amplitude by increasing the distance from the magnetic field source. Each point then has been represented separately in a diagram where you can see that there is a certain decay characterized by the experimental data in black, and the red is the polyfit. By using an exponential function and the data, it's possible to reconstruct the function e to the minus alpha z by considering the fact that we have experimental voltage signal that allows us to create a polyfit to create an exponential one. You can see on the right side the error between the experimental data and the exponential function from where we carried out the first parameter of the electromagnetic wave, which is alpha 7.2714 Nepper over meter. The same thing has been done for what concerns the phase shift, because even if it's not so much visible in this diagram, the sine wave travels its phase shift by increasing the distance from the magnetic field source. As a matter of fact, in the diagram on the right side, this appears like in a linear fashion. We want this linear fashion because it is included in the expression of the electromagnetic wave. And by using the same analysis, we can carry out the value of beta equal to 0.7905 radians over meter. Don't get confused by the fact that we have a plus sign here because it looks like this part is divergent during the space. This is not possible because in a lossy media, the electromagnetic waves are damped. In reality, this component propagates towards the negative direction of Z, which makes this product negative, as well as this product. So now we have identified the electromagnetic wave because we have figured out the voltage maximum, which is located in the source position of the magnetic field. We have alpha and beta, which characterizes respectively the exponential decay and the phase shift. If you have any questions, please put your comment on the bottom and subscribe if you like it. Forward me any questions or opinions that you have about my video. I will be more glad to comment on it. Thank you so much. Have a good time. Bye. So I would like to take this opportunity to forward my special thanks to Lab Center for providing me a sponsorship and by giving me a free licensed software for PCB design, a powerful bench that allows you to simulate and design an electronic circuit board. For example, I would like to show you their website. This is fantastic. You can navigate in different options, and this is so famous, this software, and powerful that one of the most important institutions uses the Royal Navy, Continental, University of Southern California, Lockheed Martin, and the Florida State University. Take the chance to navigate through the website. It's full of videos explaining how to use products, how to create paths, how to create the vias in a very efficient way that connect copper through electronic components. In the PCB design, you have the capability, the possibility to watch a lot of videos on how to solve many problems for that. The circuit simulation is what we have done today by using the frequency response analysis between a series and parallel configurations. In the Visual Designer, you have the opportunity to link your code made in Arduino Raspberry Pi with the design, with the schematic view of your electronic circuit. If you go forward, you can choose different package configuration depending on the amount of pin that you are using in your design. And at the same time, what kind of analysis you want to perform. It's full of resource, full of demo. I mean, if you want to become a professional electronic designer, then use Proteus. All right, thank you so much, guys. I hope you enjoy my video, and I hope to see you soon in the next one. Bye.